Dr. Phys, Theoretical Physics. In our previous section, we looked at differentiation of complex functions, and we found that we had an unambiguous definition for the derivative provided these relations here are satisfied, the Cauchy-Riemann conditions. Well, the question we ask here is integration unambiguous? And we're going to see that that has to do with path independence. To understand that, we want to look at something important, and that is called Green's theorem. Now, Green's theorem will come in naturally in our discussion. We're going to start, first of all, with the idea of integration, where we have a complex plane, where you have here the real, x's here are real, and here you have I times y. Y is real, but then the I makes the I-Y combination here imaginary. So here, when we integrate with a variable z, which has an x and an iy, then you're integrating here with choice. How do you get from the z1 to z2? Like when you do an integral, you go from x1 to x2. All right, well, that's along the x-axis. You don't have this degree of freedom, but if I go from z1 to z2, well, I can get there different ways because I have x plus iy. See, I have a horizontal and a vertical. Well, if I go c1 path and then I go c2 path, notice that here, if I flip this the other way, then I'm going to call this path C2 prime, and that's going C2 backwards. And I come down here and look at this neat little observation. If I go C1 and if I go C2, all right, that's neat. That's two ways to get from 1 to 2. I'm going to go to C1 and come back C2. And when you look at the backwards one here, that one there with the C2 prime is equal to negative going the other way, because if you flip the limits of integration, you get like a minus, you get a minus sign there. So when you do this, you can then add this one with the backward one by putting this on the other side of the equation. You get this neat result that for the path to be, well, let's say the integral to be well defined where the path doesn't matter, that means if you go all the way around a loop like this, you got to get 0. So that's a neat way to see that the integration is well defined in an unambiguous manner. When I say well defined, I mean I want to get the same answer by taking different paths from 1 to 2. Well, that'll be the case if I go around a circle or a loop and get 0. So let's look at the integral. We set the integral up, and I'm going to set this up to do this loop integral, and you may have guessed it, I'm going to demand that this be the case, because if it is the case, then I can integrate along any path, and it's cool, and we have a well-defined definition of integration, unambiguous. So here's the f of z, which is u plus iv, and then dz is dx plus I dy, following from our previous section. So if we do the integral here, we like to separate out the I so that I have all the imaginary stuff with the I and all the real stuff here. Now remember, whatever hits the I is real, but when the real couples with the I, then that's your imaginary part. And so here's your real part. So I go u dx, and then I have I times I is minus 1, so I have then minus v dy. That takes care of the real part. Then when I have I times v dx, and I have I times u dy, I have here the imaginary part, I times this. So I have two integrals to look at, and they have this general form. I have some L function with my dx plus some m function with the dy. This is like the general result here. L would be u and m minus v. So I want to study this and see when this integral is 0. What are the conditions? And this is Green's theorem to see what the conditions are. Here's a neat little way of seeing it. Let a vector B be equal to L I hat plus M J hat. And our R vector is our usual radial vector, x I hat plus y j hat plus z k hat. And if you take the dot product of these two, I dot I is 1, and, well, first you want to make this a dr, so we'll do that first so we can get this. But you can see how it's going to work. L will have the dx with it, M will have the dy. So let's do the d first, the differential, all right, and then take the dot product. So here we have the vector b as before, and we have the dr getting set up to do our dot product so we can get our integral. So this is b, dot it with this, gets you L times your dx plus M times your dy, because the only thing that survives here is I dot I hat dot I hat, that's 1. I hat dot j hat 0, so you have to have j hat dot j hat. That gives you then M with dy, and there is no k hat over here, so we're finished. That's it, and that's what we have up here. Now we remember something from earlier in our course, that if we have a vector b, you see, dot it with dr, which is what we have here. So this is a b vector, dot it with dr. That Stokes' theorem tells us that if you go around the loop, here my dr is replaced by a dl. It's just a variable of integration, not a big thing there. So by going around that loop, I know that by Stokes' theorem that's del cross b dot dA, where dA is here an area, a little differential area. dA is defined by the area, and the vector here is perpendicular to the surface, so this is, in this case, going to be a dx dy in the plane, all right, because I just have here a loop in the xy plane, so therefore the area orientation is perpendicular, it's k hat. So when I do this dot product with that cross product here, I want the z component of the cross product, because the k hat will project out when it dots with the del cross b, the z component. And if you remember, the z component in your determinant is partial of here by with respect to x minus the partial of bx with respect to y. Now, it's good perhaps to stop the video at this point and write down, refresh your memory on taking the del cross b as we did earlier in our course, to make sure that you are convinced that this is correct before we go on. Then once when we have this result, what we're going to do is make a connection with what we have for the L and the M. See, by is nothing more than M, and bx is simply L. So if we go and do that, the partial of by, that's your M, so you put your M there with respect to x, see, your derivative, and then your bx is your L. Well, this is Green's theorem, which I have boxed off here for you. That's Green's theorem. And to make sure that our integration is path independent, if I come around the circle or a closed path, I get 0, I demand that this vanish in here. And I apply that twice now, because I have two of these to do. So I need to apply this twice, and that's what we're going to do here. For the first one, L, remember L is what is multiplying the dx, so that's u, and M here is minus v. So when I apply the conditions that I need here, this condition, I then have the partial of M with respect to x is the partial of the negative v with respect to x, minus the partial of u, that's my L, with respect to y, has to vanish. But that's the same as if I bring one of these on the other side and then multiply by a negative, I'm going to get the partial of u with respect to y on this side, see? Or I don't need to multiply by a negative. I just need to add this to the other side, and then I got it. So I just add this to the other side, partial u with respect to y, and then that's equal to, you just pull the negative sign out. So that's all you have to do. No multiplication by any negative thing here. Just simply add that to the other side, and you're finished. Now notice that that's one of the Cauchy-Riemann conditions, because if you take the u, the first variable, when you have u and v, and you then take the derivative with respect to the second one in terms of x and y, a second one, and then you have them flipped. In other words, first variable with respect to the second variable, when you're thinking of the pairs uv, u comes before v, x comes before y, and when you flip them like this, you have the minus sign. So we go to the next one. The next one over here is v is L, and u here is m, and we apply the Green's theorem again for this other part, the second one. So I have the partial of m, that's the partial of u, see, with respect to x, minus the partial of v with respect to y. Now I add to the other side of the equation, this one here, and I have this equation, which is the other Cauchy-Riemann condition, because here I have u comes before v, x comes before y. So when I have it like that, it's plus sign. Here when I have them swap, the u and you see the y and the v and the x, I have the minus sign. Now that's too good to be true. The fact that the same conditions that save us with differentiation, you have the same conditions that save you for integration. That is too impressive. That is too cool. That the Cauchy-Riemann relations, the same relations, takes care of derivatives and takes care of integrals. So that result, very, very, very powerful. I'm going to ask you here for a practice problem to show that you can apply these relations to these two functions and they work. And then for homework, you're actually going to take the f of z to be z to the nth power, and if you can do a power of z like that, and you know that powers of z, Taylor series expansion, you are covering a lot of functions. So you're going to show that they're analytic, all powers of n, say z to the nth power, analytic. And if that's the case, cosine, sines, all kinds of power series with functions that can be represented as power series are all cool functions. They're all going to work. Very, very powerful discovery here that the same relations save us for differentiation and integration.